All right, hello, and welcome to the fifth lecture of PDEs. And today, after having first set the stage with some general analysis in d equal to 2, we shall focus on a specific equation. Uh, and we are going to speak about the wave equation today. So, the wave equation is, sorry, so we are in two dimensions. So this acting on psi xt is equal to 0. And we're going to specify Cauchy data like we have been doing. That is psi of x0 is equal to some alpha x. And del psi del t at x0, this is equal to some beta x. And we are doing this for 0 less than x less. Now, what we shall show is that this uniquely determines the solution in a in this domain of the xy plane. And we shall also determine what this unique solution is, okay? So we shall show this uniquely determines solution, the solution in a domain of the xt plane, and we will find the solution. Find the solution. Okay, so first off, what are the characteristics? These are xi xt is equal to is x minus t, this is c1, and eta xt, this is x plus t, which is c2. These are straight lines. At 45 degrees to the x-axis. All right. Okay, so we have straight lines at 45 degrees to the x-axis. Now, suppose you have an open hypersurface, which is at t equal to 0. This is never going to be parallel to these family of straight lines at 45 degrees at any point. Okay, so let's write this down. So open hypersurfaces say 0 less than x, 0 less than 1, t equal to 0 are never parallel to the characteristic. At any point. Right? So the solution can be determined in the neighborhood of each point on the open hypersurface. So solution can be determined. All right, so as we have seen, we can rewrite this OPE, this PDE as d2 del zeta xi del eta of psi is equal to 0. And this immediately gives you a solution of psi is equal to f1 of xi plus f2 of eta. And the Cauchy data would essentially imply the following. It would imply that so this you remember is at t, right? So psi is equal to f1x plus f2x is equal to alpha of x, and also del psi del t at x0 is equal to minus f1 primed x plus f2 primed x is equal to some beta of x. So remember what exactly this was. You need to just keep in mind the following. How did I get at this last equation? So del t is what? Is del zeta del t del zeta. If this is expressed in terms of eta. So when this is just a function of zeta, this is just minus del zeta. So when you have, and similarly, if this were a function of just, so yeah, this is just going to be this guy, because you remember that psi is x minus t and eta is x plus t. So essentially, yeah. So let me not write it in this way. This is a little weird. So yeah, let me just re-express it like this. So this is del t is del zeta del t into del zeta plus del eta del t del eta. So this is actually minus del psi plus del eta. So del psi del t acting on, so this is going to be minus del zeta plus del eta acting on f1 of psi plus f2 of eta. So this essentially means that this is minus f1 of primed of psi plus f2 primed of eta. Okay, this is how I get this. Okay. Now, what can we do? Now let's do the following. We can actually integrate this equation, this second equation, at some arbitrary point. So integrate this equation at at some arbitrary point x naught, which is in x and y. So this then what is it that you get? You get minus f1 of x plus f2 of x is equal to some integral x naught to x beta of x primed from some constant c. Okay, so you can get f1 of x is something, some alpha x plus maybe minus x naught to x beta of x primed dx primed minus c, and f2 of x is going to be, so we can parameterize this as plus x naught to x beta of x primed dx primed plus c. So what have we got? We have got that our our solution to this wave equation is of a form f1 of x minus t plus f2 of x minus x plus t, and this essentially becomes half of alpha of x minus t plus alpha of x plus t plus something where this is going to be x minus t to x plus t into dx primed beta of x primed. So this solution is now determined for the region in which alpha of x minus t and alpha of x plus t are known. And so that is what the solution to this equation is. All right, so yeah, so we shall say more about this now. So yeah, so what we do have is that we know the solution now. This is determined for in the region where these functions alpha x minus t, alpha x plus t, these are known. Now from I mean boundary conditions, what do we have? From boundary conditions, we have that alpha x is known from 0 less than equal to x less than 1. This is from boundary conditions. So what is the known region in that case? So the known region is going to be the intersection of these infinite strips. So this region essentially 0 less than equal to x minus t is equal to 1 and 0 less than equal to x plus t is equal to 1. This is the known region. Right. So you see that the finite, so this is a finite area square. This region is this finite area square, just symmetric, which is situated symmetrically about x. I mean the x-axis or the t equal to 0. Now, for a generic solution, for some interval, for a generic interval, say, x1, x2, the solution is only meaningful when uh, solution is only meaningful sorry meaningful when this happens, right? When x1 is less than equal to x plus minus t less than equal to x2, this determines a rectangle in this RT plane. But when you take x1 to go to minus infinity and x2 to go to plus infinity, in that case, the spatial uh, domain is in spatial domain is infinite, and the rectangle uh, so as you take this guy out to this side and this guy out to this side, the cross sections will increase, so they'll become bigger and then bigger and bigger. I mean, unless when you go, so until that you go out to infinity, and in that case, the whole of the xt plane is determined. Everywhere, and solution there is going to be determined everywhere. Spatial domain is infinite. Rectangle covers the entire RT plane, and solution is determined everywhere. If these initial conditions, like in the case that we have just looked at, is specified in a finite segment, then one needs further information if you want to determine the solution elsewhere. So for example, you can maybe give boundary conditions for all times, like something like so let's just say more information required to find full solution if x1 x2, this is uh, this is a finite interval. For example, you can give boundary conditions for all times, like psi of x1t is some c of t, psi of x2t is some d of t, and so on and so forth. Now let's simplify the analysis. Then what are we going to do? Let's take the case where x1 equal to 0 and x2 is infinity. Okay. So so then it's sufficient only to give one boundary condition at x equal to 0. Sufficient to give one boundary condition at x equal to 0. Let's say, for example, you can think of psi of 0t. Let's say this is 0 for all times. And what we are going to do is we are going to replace our problem by one for which the initial boundary conditions are prescribed for all x. So replace problem by one for which initial conditions are prescribed for all x, that is minus infinity is an equal to x less than infinity, and psi at t equal to 0 is equal to a of x, psi del t at t equal to 0 is b of x. So these a of x and b of x, a of x is equal to small a of x that we had earlier, and b of x is equal to small b of x that we had earlier for x greater than 0. But unknown for the moment for x less than 0. Okay. So the solution is what? The solution is going to be that, so this is what we found earlier. Psi of xt is going to be half a of x plus t plus a of x minus t plus minus t to t b of x primed dx primed. So that is the solution. Now to satisfy the boundary conditions, uh, to satisfy boundary conditions, we must have a of t plus a of minus t plus integral minus t to t b of x primed dx primed. This, as we have seen, this has to be equal to 0. Look back at the boundary condition that we have here. So if this has to hold with this particular boundary condition, then this has to be true, right? So thus, this is going to be equal to 0. Now, what can we say? Now, since the integral is an odd function of t, a of t must also be an odd function of its argument. All right, let's clarify this a little bit. Okay, so let's do a little bit of so what we are going to get is the following. So we're going to get a of x is equal to minus a of minus x. So let's see how you can get this instead of trying to give you some slick argument. Let me just do this for you. So you have a of t plus a of minus t plus integral minus t to t b of x primed dx primed is equal to 0. Now let's interchange t and minus t. Okay, so a of minus t plus a of t is equal to integral t to minus t b of x primed dx primed is equal to 0. So what have we done? So we have just interchanged the variable. So let's just actually try and okay, let me just give me a second. Let me try and squeeze this in a little bit. Okay, so this, what have we done here? So this just is a change of variable, change of variable. T2 minus T, okay? Now, so this, again, this is what? A of minus T plus A of T minus integral minus T to T B of x primed dx primed is equal to 0. So that means, so you can take this equation. Sorry, you can take this equation, and you can take this equation, and you can add them, right? So that would just mean that A of t plus A of minus t is equal to 0. So that just means A of t is equal to minus A of minus t. Similarly, the integral of this guy is also equal to, sorry, the integral of this guy is also equal to 0. So that also simply means that b of x primed is equal to minus b of minus x primed. So this is what we get. So this one is because of integral of minus t to t b primed of, sorry, b of x primed is equal to 0. This essentially implies this, right? So this has to be an odd function, right? If this is symmetric about something and this goes to 0, so that means it has to be an odd function. Very good. So A is an odd function, B is an odd function. So this holds. So the requirement is the following then. So requirements are A of x is equal to minus A of minus x, and B of x is equal to minus B of minus x. And then these two requirements, along with A of x is equal to small a of x, which is given. And b of x is equal to small b of x for x greater than 0. This determine a and b for all arguments. And hence what you have is that you have a solution. So you have a solution that holds for all x and t. So you see what we have done. So we had first, we had looked at the problem when we were trying to determine what the wave equation was, and this data, Cauchy data was given to us at a finite interval. We solved the equation, and this was by means of these uh, zeta, xi, and eta, the characteristics which are at 45 degrees. Uh, and what we had said is this thing was actually prescribed for an open hypersurface, um, you know, x of in uh, this regime and t equal to 0. So this was never parallel to these curves. So the methods that we were employing in our general discussion that were valid. So then we can just rewrite the equation in this form, and that gives us a solution of this form. And the Cauchy data just becomes in this case, I mean, t is equal to 0, so it's f1 of x and f2 of x equal to some alpha x. And the other thing was that minus f1 primed of x plus f2 primed of x is equal to some beta x. So we integrated this equation to get f1, f1 minus f2 from here, and then we constructed one f1 and f2 individually were. So this just so then we plugged it into what our differential equation was, and the solution was known for this was what psi of xt was. Now, alpha of x and t was known from 0 to 1. Alpha of x was known from 0 to 1. So what we saw is that we know this in this regime where x minus t goes from 0 to 1, and x plus t goes from uh, 0 to 1 as well. So that in this particular regime, this was known. So that actually amounted to looking at this shaded region that we have out here. So our solution was valid only in this place. Okay. So if you have a generic point x1 x2, the solution is only going to be meaningful when you have when this lies between so x plus minus t is going to lie between x1 and x2. Now we said that this was for this region. If we make this longer, this would grow larger and larger, and when x and x1 goes to minus infinity and x2 goes to plus infinity, then the spatial domain becomes infinite, and the rectangle covers the whole of the RT plane, and the solution is then determined everywhere. Suppose we had a finite interval. In that case, there would be more information required to find what the full solution is. For example, you would need boundary conditions at all times. So x x psi of x1 and t would be some c of t, and psi 2 at x and x2 and t would be equal to some d of t. So for example, let's look at one such example and try to clarify this. Let's look at the case where psi x1 equal to 0, but x2 I have gone off to infinity with that. So in that case, it's sufficient to give a boundary condition, maybe just at x equal to 0. Okay. Then what you do is you write the, so for example, the thing that we're looking at is psi at 0 and t is going to be equal to 0 for all t. Okay. So what are we going to do for this? What we are going to be doing is we replace the problem by one for which the initial conditions are prescribed for all time. So psi at uh, t equal to 0 is a of x, del t at t equal to 0 is b of x. And so we know that psi, big A is equal to small a of x, the one we had earlier, and big B is equal to small b of x for x greater than 0. But we have also this thing where we do not know things at x less than 0. What we do is that then we go through this and we try to uh, write down the solution now, which is the thing that we know from earlier, but we also need to satisfy this extra extra boundary condition. So for that, that puts more requirements on A and B. And then if we know what these these entail, then we will for example, in our case, this means that these are odd functions. uh, so this x, a of x and b of x are odd functions. From the knowledge that we know a of x at for all x more than 0, at a of x and b of x, and augmented with this extra thing out here, then now you would be able to determine this for all x and t. Okay, this is how you are going to solve this, the wave equation. So this was, a bit short, but what we will do next time around is we shall try to look at other equations and see how you can go about trying to understand, firstly, the one-dimensional diffusion equation, and then the, two-dimensional Laplace equation. And then we'll see a few more, general things that you can say for, um, what sort of boundary conditions are required for what equations and so on. So, all right. So that's it for now. And again, we shall see each other soon again.